Welcome back. In this particular case, we have a molecule that's containing nitrogen, right? So just like how we saw in the previous video with the nitrogen, nitrogen must always contain 3 bonds, okay, attached to it. And then it also contains a lone pair of electrons. Now, if one of the bond attached to the nitrogen is a double bond, then you put the lone pair of electrons on the outside, but if it's single, then you put it on the inside. Now, this nitrogen is attached to 3 bonds, like it's supposed to be, and there is no double bond attached to the nitrogen, right? One of them is not a double bond, so that means we can put the lone pair inside, and the lone pair itself is a bond that can be moved around. It's like a double bond in a 2-bond system, okay? So unlike you have a system that's purely carbon and hydrogen, things work a little different for compounds containing nitrogen. So to determine if it's aromatic, as I always said, first do the Huckel's rule. That'll eliminate a lot of the mental hassle, but you can always be sure this will satisfy, and I would still make you go for it, all right? So this is a bond, so this is 2 electrons, 2 plus 2 plus 2, 4 plus 2, 6 pi. Yeah, you sure can. We've done enough examples to know 1 plus 2 is 6 pi, so Huckel's rule is met, right? Now it's a question of double, single, double. Like I said, this is double, this is single, and so I'm going to do it in different color so you can see it. So this is a double, single, double, single. This is a double bond, so it's double and single, right? Good. So the D/S has worked. So now let's actually take a different color, maybe a pink, okay? Now, when it comes to nitrogen, you don't start moving through the entire molecule. You move one thing at a time, and when electrons are lost, okay, that element must get a positive charge. When electrons are gained, the element must get a negative charge, okay? So I'm going to redraw this molecule for convenience because I don't want to, re-emphasize over that molecule that is congested looking for time being, okay? All right, so I'm going to get my red, okay? So you can literally start anywhere you want, but I always prefer to start where the lone pair is. So if I move this lone pair here, this bond doesn't go here, it goes here. Why? You'll see it in a minute. Now, this is the first of the resonance structures. Now, like I said, this nitrogen is an element. It's lost both its electrons, so it gets a positive charge. The electron in terms makes a bond here because it's moved there. This bond is moved into this carbon, but because you lost a pair of electrons, a pair of electron is gained here, and that gets a negative charge, right? Because this bond right here has 2 electrons, and those 2 electrons are moved into this carbon. It's like a repository, if you would think of it that way. It's stored as grains in this particular carbon. This is the first resonance structure. You don't even mess around here, you go here. Now, there's this bond that's untouched, right? So now I'm going to move this pair of electron here, making a bond. In turn, this comes to this carbon. It's important that you pay attention to where everything else is going. So this is the third resonance structure. And again, we have not disturbed this bond or the nitrogen. It's still intact, okay? And so this bond is now come here, and that means this bond has now come here as a negative charge with the lone pair being here. Now we can continue this process. This could come here as a bond. That means what would happen is, right? What would happen to this structure right here? So let's go ahead and draw it in a different color. Okay, so if we move this here, okay, we cannot move a positive charge, right? We have to move this in here, right? So let's get a different color. I don't know what other color I can use. I guess I'll go back to my pink, right? So the positive charge is still there because we can't move a positive charge. It's not that easy. So this bond stays right where it was, because now this is a negative charge that's becoming a bond, but then this bond has moved here, so the negative charge on the pair of electrons here, right? So, you know, you can continue to do this process, and then you would see that you would keep continuing the cycle forever. And then, you know, that's essentially what it is. So if you do this here, okay, if you can continue this process, this negative goes here as a bond. That means this goes here. I'm going to get my handy dandy blue. So this is another resonance structure. So again, if I were to test you, I will just have you do this as a separate component in a multiple choice format. So what would this look like? Let's draw everything. It's just important that you take one step at a time. Sometimes people tell you take one step at a time, and I think this is where you really see that in action, okay? All right, so if you keep doing it, eventually you will end up where you started, all right? You don't need to do it, so it also follows resonance. So this fills all three rules. It's aromatic, all right? So the nitrogen containing compounds are a little bit tricky, but it's not overly difficult. What I want you to do is watch both the videos, actually all three videos. The one with carbon and hydrogen is easier. The one with nitrogen is a little tricky. But if you don't understand this idea of negative lone pair and a positive charge, you're going to have trouble throughout the course, because you would be asked to draw resonance structures of a particular compound, and you should know, because this is the heart of organic chemistry, okay? You should be able to do this, and otherwise it makes things very difficult. So we might spend more time in class on this particular concept to help you get over that, and then we can move to other concepts which are much more manageable. All right, so I'm going to stop here. This is all I have to share with you about aromaticity and finding whether a molecule is aromatic or not. So I'll see you with another video series very soon. Stay tuned.